Picture our solar system about 4.5 billion years ago. The inner rocky planets are just forming and cooling off. Some rock is still hot enough to flow like honey. Mercury is only a couple 100 million years old, and Venus is only a few 100 million older than that. Even Earth, which is our home planet, isn't quite done baking. It has 300 million years into its existence, and it's just starting to cool off enough for solid ground to form on its surface. And then wham, a huge asteroid slams into the young planet. Rock and dust from the collision blast blasts thousands of kilometers up through the atmosphere, and some of it never comes back down. And over the next few 100 million years, this happens again and again and again and again. Welcome to the late heavy bombardment, one of the most dramatic periods in early solar system history. This period of intense asteroid and comet activity likely started around 4.6 billion years ago and lasted until about 4 billion years ago. During that time, Earth, along with the other inner rocky planets, was struck by many more asteroids and comets than at any other time in their existence. This bombardment reshaped the surfaces of the planets and may have delivered the water that makes Earth habitable. It also probably brought here the molecules that became the building blocks of life. So what caused this late heavy bombardment? Scientists think it was a once-in-a-solar-system event that affected not only Earth, but Mercury, Venus, and Mars. And it could have been caused by something as exciting as planet migrations. For decades, astronomers weren't even sure if the late heavy bombardment actually happened. That's because the evidence for it comes from studying meteorites, rocks from the moon, and chemical evidence on Earth and the other planets. And each piece of evidence tells us a little bit of a different story. Let's start with meteorites. Most meteorites are stony rocks called chondrites. They come in all shapes and sizes, but they're all pretty ordinary. You can find them on the surface of the Earth, on the Moon, and even on Mars, but there's a problem. All these rocks look pretty much identical, which means you can't tell how old they are just by looking at them. And so scientists instead had to get creative. One way of dating meteorites is by measuring how radioactive elements within them have decayed over time. You see, radioactive elements break down into different, more stable elements at a steady rate. So if you know how much of the original element there is left, you can calculate how much time has passed since the meteorite formed. This type of dating works really well for some meteorites, but not others. Take ordinary chondrites. These are the most common type of meteorite, and they've got plenty of radioactive elements inside of them. But as far as scientists can tell, they haven't changed at all since they formed. Their surfaces are pristine and unmarked. That means they probably fell from space very recently. None have been dated to be older than a few million years. But there's another type of chondrite out there, the carbonaceous chondrites. Unlike their ordinary cousins, these rocks show signs of having been altered by water, and that means they must be ancient. Based on radiometric dating, scientists now think that most of them formed 4.5 to 4.6 billion years ago. And that's the same age range as the oldest meteorites scientists have found on Earth, on Mars, and on the Moon. Now let's move away from meteorites and talk about the Moon. The Moon's surface is covered in craters, and scientists use crater counting to figure out how old the surface is. That's because as time goes on, new craters form as fresh impacts carve out new holes. So the fewer craters there are, the younger the surface. But a big problem is that the Moon doesn't have a global magnetic field to protect it from being hit by charged particles in the solar wind. And those particles gradually wipe away the evidence of impacts. So the cratering record scientists observe today is probably much older than it looks. To try and figure out just how much older, scientists have studied the chemical makeup of lunar samples brought back by NASA's Apollo missions. They found that many of the minerals in the lunar soil were heavily irradiated, meaning they were exposed to lots of high-energy particles. So the Moon's surface had to have lost a big chunk of its protective atmosphere very early on, exposing it to the full force of the solar wind. If this happened around 4 billion years ago, then the surface would actually be much younger than it looks. And that matches what we've learned from meteorites and the oldest rocks on Earth. All this evidence together led scientists to hypothesize that the late heavy bombardment must have taken place between about 4.6 and 4 billion years ago. And during that time, Earth, Mars, Venus, and Mercury were hit by an unprecedented number of asteroids and comets. But why did this happen? Well, one hypothesis is that giant planets migrated inward, scattering icy objects that were floating in the outer solar system. In fact, some versions of this hypothesis say that this migration may have also explained the origin of Earth's moon, according to computer simulations. Giant planets moving through the disk of dust left over from the solar nebula would have gravitationally attracted clumps of dust and gas that eventually formed the moon. Now, this hypothesis is controversial. For example, samples returned by NASA's OSIRIS-REx mission suggest that the asteroid that ultimately formed the moon was pretty ordinary and didn't come from the outer solar system. But the idea of giant planet migrations does seem to explain why Earth was hit so hard, and not just Earth, but the other inner rocky planets too. You see, simulations of this process usually include more than one planet, and the results suggest that multiple protoplanets or planetesimals were flung towards the inner solar system and crashed into Earth and the other planets. Simulations have also shown that a giant planet migrating in from the outer solar system would have pushed Earth a few million kilometers closer to the Sun. And we know from studying the orbits of the outer planets that the gravitational influence they exert on one another is strong enough to affect the orbit of Earth over millions of years. So giant planet migration could explain the unusual alignment of the inner rocky planets with one another and with the Sun. Of course, this is just one hypothesis, and scientists are still debating whether or not it's true. But whatever the cause, the late heavy bombardment was a key moment in the timeline of our solar system. It was the last major event that shaped the surfaces of Earth, Venus, Mars, and Mercury before they were habitable or at least liquid water stable. It also probably delivered the organic molecules that became the building blocks of life here on Earth. Take amino acids, for instance. These are the building blocks of proteins, and they're present in all living things today. But they're pretty fragile and tend to break down when exposed to radiation, heat, and UV light. On Earth, the only amino acids we find are protected deep underground where they can't be reached by cosmic rays. But in 1970, scientists found a group of amino acids known as the Murchison acids in a meteorite that fell in Australia. Those acids hadn't been detected on Earth before, and they were only found in carbonaceous chondrites that are more than 4 billion years old. So it looks like they were delivered to Earth long before life evolved. It is possible that these molecules were produced when the interstellar dust that formed the solar system was zapped by cosmic radiation. Or they could have formed in the dust after collisions with comets or asteroids. Either way, they came from outside of Earth, and the late heavy bombardment would have been the last period of intense delivery from the rest of the solar system. The late heavy bombardment literally reshaped our world. It cleared Earth's primitive atmosphere and helped it cool to the point where liquid water could exist. It may have given Earth its moon, and it brought here the molecules that became the building blocks of life. So while it's not the first event in Earth's history, it might be the most important. Thanks for watching this episode of SCI Show Space. If you would like to learn more about the solar system's rocky planets, we've got videos that you can watch next.